Oh, okay. So now
What's the color?
it's greener.
Is it green?
Yeah. So now I want to explain definition of associative variety for general rule A. So for this I have to recall some notations. So we have a map which satisfies certain properties, and also a translation operator which is for if you have a conformal vector, it's the same as L minus 1, which behaves as a differential. So this is the same del V n equals to minus L V n minus 1. And we have also a vacuum vector which goes to identity map. And what else? Maybe this is all I need. And so and also any vector. So this is the same as V minus 1. So something like this. And we consider following a quotient space. So this should be the quotient space. This corresponds to the quotient space I considered in the first lecture, which is defined as the following. So C2V is just a span A minus 2B. And this is the same as span of A minus NB is A. And so what this should observe is that this quotient has a structure of as a Poisson algebra. Where the multiplication is given by minus 1 product. The minus 1 is a minus 1 here. And Poisson bracket is the zeroth product. So you have somehow strange Poisson algebra, and this is actually a finitely generated Poisson algebra in usually. So you can consider corresponding spectrum. And this is what we call the associative variety. And so this quotient space is defined by Z, but it actually goes back to Feigen-Fuchs. So let me explain this example. So let Vc be the Virasoro VOA at central charge C. So this is an induced representation of Virasoro algebra, induced from one-dimensional representation of. So here we have Ln with n is greater or equal to -1, not 0, and also a central charge. The central charge acts as C, and this goes to 0. So this, so as a vector space, this is U of Virasoro with which have index less or equal to -2. And so this has a structure of VOAs. And this structure is determined by the image of the so-called conformal vector. So Vc has this minus this vector, and this goes to a generating function of Virasoro algebra. And this completely determines vertex algebra. And so for this case, this quotient space is what? It's a quotient by So this space. So only this remains. So this is so the associative variety is just a affine space A1, and if you consider the simple quotient, then the associative variety is the subvariety of C. So this is Koenig. So this is 0 of the whole space. And the theorem. So this is again a special case of more general statement. This associative variety is 0 if and only if central charge is the central charge for the minimal model. Yeah. But this statement is rather, maybe it's trivial, but they stated for a general modules. So, it's highly reduced. Yes. It's highly reduced. Yes. So. And actually, this is the same as LC is not VC. So if this is reducible, you have a singular vector, and the image of a singular vector here is non-zero. So the zero locus must be the point. So I explained the example of when the variety is zero for affine VOA and Virasoro. For both cases, this zero variety condition characterize the nice representation, namely integral representations and minimal series representation. So we can, using this associative variety, we can generalize this nice representation or nice VOA by defining, by saying that if associative variety is zero, then we say V is least or C2 cofinite. And one can show that this condition is the same as you can. So any VOA is naturally a filter. So you can consider corresponding associate graded, which is naturally an algebra. In fact, it's a differential algebra. So you can consider a corresponding spectrum. And this is the same as this whole space. Spectrum for whole space is zero. So this is very natural finite in this condition. So in vertex algebra theory, in most papers they assume this condition to derive some properties. Now we are interested in vertex operator algebra, which come from 4D theory. So which would associate variety should be Higgs branch. So what property is expectation for Higgs branches? So associated variety, as I defined, is just a Poisson variety. But Higgs branch should be irreducible as variety and also symplectic in its smooth locus. And also it should have a finitely many symplectic leaves. So this satisfies this kind of finiteness condition, which is much more general than being zero. It's always conical if yeah.
So in other words, the algebra is graded.
Yes.
And what is the grading?
The Virasoro. So, in connection with for this theory, it makes sense to consider VOA with having that property. So let's say a VOA with quasi-Lis. If associated variety has a finitely many symplectic leaves. And what can we say from this constraint? So we can say the following. So if VOA is quagiris, then the character of V, which is defined as a trace of this operator, satisfies a modular linear differential equation. There's a certain differential equation which is satisfied by a modular form. So in particular, this implies that this converges to holomorphic function on the upper half plane, and also because the solution of modular linear differential equation is closed under the action of SL2G. It lies in finite dimensional representation of SL2G. So it means this character satisfies certain modularity property, and so is the Schur index, if you believe this conjecture. Because if the Higgs branch is with conjecture is true, this should have finitely many simple leaves, and then corresponding character, which is the same as Schur index, satisfy modular linear differential equation. So it has a modularity property. And this is something physicists wanted to show, and this is somehow only way to.
That's modular rational level they satisfy.
Yeah, of course, yeah. But this is more general. Certain differential equation. So it has a property that solution is invariant under the action of SL2G. Under the action of SL2G. Invariant, yeah.
But you're saying that this guy is not invariant, but just something slightly weaker focus in the generates finite dimensional space on that.
So
all solutions.
all solutions, yes. Yeah, maybe I just say a few words for the proof. So it's not so difficult. So what you want to show is the space, the dimension of space of one-point function on elliptic curve is finite dimension. So the space of conformal block is finite dimensional. And so the Zhu introduced this algebra to prove this property for general VOA. So this means this quotient. This is more or less the same as this quotient space. So meaning that there's a surjection from here to here. And there's a theorem of Ettinghoff and Schedler, which says the following: if Poisson,
I think you're with C in Schedler's name. It's SCH.
Schedler. So if Poisson algebra, so let R be Poisson algebra. If a spec of R has finitely many symplectic leaf, then this quotient space, or there is Poisson homology space, is finite dimensional. So if you admit this theorem, it almost follows from the definition.
Are there examples for this example modular form?
Yeah, there's an example I showed you the modular form, ratio of beta functions. In general, this is so in general, this Shua index or the character is not really modular, but quasi modular. It's modular for the case for the admissible ones. It contains tau derivative of Eisenstein series. Okay, so now I want to explain more examples. So
Right, and the fact that the dimension of the space one-by functions of the torus is finite, so you think that the fact that it's equivalent to a theorem is it somehow obvious?
this is
Your formulation was that character. No, I'm not thinking about this problem. I think your theorem was that the character of your algebra satisfies the differential equation. And now, instead of that, you're proving this fine dimensionality of this space of one-point function. So, is it obvious that it's the same statement?
so maybe I didn't explain it. So this character belongs to this space,
Yes.
and if it is finite dimensional, you can find it's almost obvious that you can find differential equation.
So you're actually directly proving this statement that the generates fine dimensional representation of SLP.
Yeah, you can say yeah. You can say so. Yeah. But yeah. Okay. So examples of quasi these VOAs, and also VOAs coming from 4D7. So this is something I want to explain using the rest of the time today. So I want to recall first admissible representation. So I consider as highest weight representation of G hat, or with highest weight lambda. And this is called admissible. If it satisfies following two conditions. So first, this weight is regular dominant. So this means the corresponding Kazan-Lussig polynomial is trivial. So this means that the character of representation is written as so it has a wildcat type character form. And the second condition is that the Q span of integral roots. This is a set of integral roots. So this is a set of real roots whose pairing with lambda is integer. And this is the same as Q span of real roots. So this means this is a big set. And so it contains translation part. So this is written as in terms of theta function. So it has a modular invariance property. So that's why this admissible representation has some modular invariance property. And
what is the meaning of W1?
so this is integral Y group generated by reflection corresponding to this. And the fact is that if you consider the vacuum module, so this is admissible if and only if this shifted level satisfies the following condition. P over Q. So this is positive rational number. P and Q are mutually prime, and P is greater than dual Coxeter number or Coxeter number. And here, if denominator and Lacing number is mutually prime, so our check is a Lacing number of G, which is a maximal number of edges in the decaying diagram, and otherwise the Coxeter number. And this case is called principal admissible. And this case is co-principal admissible. And in this case, integral Y group is the same isomorphic to the integral Y group of G hat. But this case, integral Y group is isomorphic to the Lagrange dual of G hat. So now the theorem states the following. So let LKG be admissible. Yeah, so because it has a modular invariance property, we expect that the associated variety satisfies some nice properties. So it's interesting what kind of associated variety to see what kind of associated variety they have. And first thing you can show, which was conjecture by Fegian. Conjecture by Fegian Frenkel. Is that this associated variety is always contained in the nilpotent cone of G. So this is very special. So we don't have this property for all representation, because if K is generic, this is the same as induced modes. Now in this case, the variety is exactly the whole space. So this property is a very special property. No. I showed the example when this holds for non-admissible case for L minus 2D4, for example. This is not admissible. So it's interesting to classify which representation satisfy this property. And if it satisfy this property, this is, so in particular, so the symplectic leaves here is just a quadjoint orbit of G, and the nilpotent element has only finitely many nilpotent orbit. This one is quasi-Lie. And classification of quasi-Lie affine VOA is not known except for SL2. Even for SL3, we don't know the answer.
Do you say this L minus 2 before is not regular? What is wrong with this definition? It's not regular?
So
Yeah, but I mean for L, what fails for L negative 2 or D4? Certainly it's integral. Is it not regular? Or what is wrong? You say that L negative 2 of D4 violates this condition. What is wrong with this condition? Is it
it's not a regular domain. So Kazan-Russell polynomial is not that trivial at all. But because of the modular linear differential equation, you can actually obtain explicit character formula, which is quite surprising. And you can actually, so this I didn't expect, but one can show that this is actually irreducible variety. So meaning that it's a closure of some nilpotent cone of G, which depends only on the denominator, on the denominator. Q of K. More precisely, not directly. No, you cannot deduce this from that.
I think even for quantitative where you kind of generalize the statement.
Right. We want to generalize this, his method, but the problem is our algebra is not Noetherian. So I don't really, there's no obvious way to generalize his argument. So more precisely, so this variety you can describe explicitly. So this is just a set of x so that adjoint of x to 2q equals to 0 for this principal case. And or by theta, so this will satisfy this condition, where this is a irreducible representation of G with highest weight theta is, which is the highest short root. So this one has highest weight highest root theta, and this one has highest weight theta is the highest short root. And so this kind of variety is not irreducible in general if this is not even. But somehow only even integer appeared, and this happen to be reducible. So this is so admissible VOA gives a family of quasi-Lees VOAs. And in fact, you can construct many more quasi-Lees VOA from this by Dunifel-Sokolov reduction. And this is what I want to explain. So let G be some nilpotent element. And then you can define corresponding double algebra. So which is defined as a Dunifel-Sokolov reduction associated with F of this universal affine VOAs. I recall that this one was an induced representation of affine Katsumori algebra, which has a natural structure of VOA. This is Dunifel-Sokolov reduction. Associated with. So this is a certain variant of Hamiltonian reduction. And what is known that the associated variety of this double algebra is the Srodoi slice at F. So this is Srodoi slice. At F, where EHF is SL2 triple, and G is a centralizer of E inside G. There's no assumption. So let me consider the Kazan-Lustig category, so which is full subcategory of category O of G hat at level K, which are equivariant under the action of GT. And so here we have this induced module and corresponding simple quotient. The theorem states the following. So this is for any k and for any f. So first for this, we have the vanishing of cohomologies for any objects. Here,
You won't say that it's zero.
oh yes. So this means this functor. I forgot to say. You can define Dirichlet-Sokolov reduction for module, and this gives a functor from the category of G hat module to the category of the module of a W algebra. And if you restrict this function to this casuistic category, this is exact. So this is a very nice functor. And for any quotient of VKG, so any quotient has a quotient vertex algebra structure. So you can talk about corresponding associative variety. And so is its image. And the associative variety of image it can be described very nicely as an intersection of the variety of V with the Schrodinger's slice. So this holds as schemes. So in particular, so this one is non-zero. I forgot to say, so if I write as a G W sub K G F, the simple quotient of a double algebra, and then associated variety of the simple quotient or any quotient is a variety of the universal one, which is the Schrodinger's variety, and which is an invariant and reduction system. So there's a action of sister contracting to the point F, and so this is invariant under this sister action, because this sister action comes from the conformal grading. So if this is non-zero, if and only this intersection is non-zero, and this happens if and only have this contains a point F, and because this is the invariant, it happens if and only if this variety contains this nilpotent obi closure. So in particular, Dirichlet-Sokolov reduction kills integral representation, because variety for integral representation has only 0.0. And So if associated variety is exactly the closure of this orbit, then associated variety is the point F by the transversality of slowly slice. And so this is least, and so is its quotient. So its quotient W K G.
I mean, you only need that this closure as a very useful component. It's like
Yeah,
a
yeah.
condition.
But we expect that the associated variety is reducible. Yeah, so this means each admissible representation produces one least double algebra, because the corollary of this statement is that the so if LKG is admissible, and so first four, and then if you take nilpotent element from this orbit, then corresponding double algebra is this. And if you apply this for SL2 for non-trivial nilpotent element, you get a minimal series representation of Virasoro. And if you apply this for arbitrary G and principal nilpotent element, you get a minimal series representation of principal double algebra. But you don't have to take element from here. If you take someone from the variety, then corresponding double algebra is quasi-Lie, because it's an intersection with nilpotent orbit closure, and symplectic leaf there is an intersection with a quadrant orbit, and it has finite remaining. So we have plenty of quasi-Lie VOAs. So the question is which one, whether they come from for this theory. But there's a paper by Shi and Yao. I'm not sure. Which says so this they come from for this theory. More precisely, so-called Douglas theory. Sergei talked about in his first lecture. If G is ADE type, and the K is the boundary admissible. So boundary admissible means that the k plus h has the following form. So numerator is the smallest as possible, the h. Maybe I want to add some number. So this is large examples of VOAs coming from 4D theory. So for this Douglas theory, so maybe I summarize what I explained today. So you have a map from for this theory to VOAs. And for this theory has several invariant at the Higgs branch. And shear index. And maybe also Coulomb branch. And you can recover Higgs branch from taking associated variety, and you can recover shear index by taking a character. But as Sergei explained this, and this is also related. So Sergei explained we can construct some modular tensor category here. And this category should be the category of module over VOAs in some sense. At least for this Douglas theories. So maybe I should be more precise. So this is not in general least or rational. So you cannot usually make sense of a corresponding modular tensor category, but you can make. So this is not. I don't think this is a mathematical statement yet, but you can make sense of it if you enlarge the category. So you have to consider all weight representations and all twist by affine wide group actions. So this generates a big category, but there you can define certain fusion product. So this is a finite category that you can quotient out by negligible modules. And at the end, you should be able to get this modular potential. At least for this Douglas series. And maybe I make some final comment. So Higgs branch. So this associated variety should be equal as varieties, but it's not equal as schemes, because this is reduced, and this is usually non-reduced. Yesterday there was an interesting paper of Shi and Yao, which says actually the scheme is in fact more important. at least for physical sense. So it certainly has more, contains more information. Okay, maybe I stop today and I explain about the classes theory tomorrow. If there's no questions.
I actually have a question. So, well, it's kind of, it's an aside question. Do you take aside questions?
Hmm?
Do you take aside questions?
Hmm?
In any case, so when we work with like representation theory of factorizations of some varieties, let's say some nice possible variety, it makes sense to consider like the restriction factor for the categories of crescendo by modules or maybe for some other nice categories. Where what you basically do, you take a symplectic leaf, and then you want to restrict your representation to slice to the leaf. And this kind of Hamiltonian reduction in the case of universal enveloping algebras is just an example. So, do you believe that such a construction makes sense for general vertex objects?
Yes, yes. Actually, this Kazanlusi category is a version for Harchandra.
Yes, but I mean, let's say that I have some arbitrary vertex algebra which is quasi-leaf, and I want to like consider its slices.
Right. Yeah.
And slice vertex algebras, and I want to have some functor which will go from some nice category of representations to the category of representations of the slice algebra. Do you believe this is possible?
Yeah. 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 It's a good point.
Where to